So we're going into OpAmp operation in order to understand A to D or D to A devices. A to D stands for analog to digital. So we're looking at an OpAmp, and without going too much into depth, we know that this is connected to some power source, and that's not a lot more than 5 volts normally, but it's connected to a power source. And there are actually 2 connections. One is negative VCC, so we get a lot of current capability when we do this. And then we are going to have a difference in voltage right here. This voltage difference is going to be amplified. Okay, so let me fix one thing here. This is V in. Okay. V in. This is the input voltage, which is the difference between the plus and the minus leads, and that's amplified. The amplification is dependent on how you configure this circuit. If you just pull the OpAmp out without any wires, any resistors connected, no feedback. Feedback means you take the output and you connect it back to the input. No feedback loops or anything. You just have the OpAmp sitting in space, of course, connected to its power. It's just going to amplify it according to the A gain, which is a characteristic of that OpAmp. Right? So it will be A times the difference between the 2 voltage leads. Now, we have a few assumptions that we always make with OpAmps. One is that the current going in to this node here and this node is 0. So if I connect an OpAmp the way you see it here, you can safely assume that all of the current is going around the OpAmp and not through it. Once you know that, that really helps a lot. You're going to be able to do a lot of circuit analysis easily because you just have that one assumption. Okay? Now, here's the other thing that is very helpful. Once you ground this voltage, okay, over here, and you create this feedback loop, then this OpAmp actually becomes self-regulating. And this voltage here will not vary by much. It will be a negligible variance from this voltage on the plus side. So essentially, you can say that these 2 voltages are going to be fixed. They are going to be equal to one another. They're going to be fixed and they're going to be equal to one another because this is set to ground, so this is going to become a ground. The way that happens requires a little circuit analysis, and that's where I will just restrain myself a little bit. I don't want to get into that. That's not the core of this class. But if you are interested, I could certainly explain that to you another time. So you should know that this circuit is causing these 2 leads to become equal. Any difference between them will be magnified, and it will be reflected in this output voltage according to this formula. Now the V in here is referring to this voltage over here. Okay. All right. So what is the purpose of this circuit? It's going to take the 5 volts. It's creating a current that's based on the resistance here. I know what the current is. You know how I know what the current is? Because I know what this voltage is. This is actually, remember I said that is the ground voltage because this is grounded, and this OpAmp is forcing these 2 voltages to stay the same. So if that voltage is 0 and this is 5, what is the current through the resistor?
Is it 0?
No, use Ohm's law. You have a resistor,
So
and
5
you
over
have
10K.
right, you have a voltage difference. You take the node here minus the node behind the resistor. That's your voltage difference. You divide by the resistor. Now you have a current of 0.5 milliamps. That 5 milliamps or 500 amps, I'm sorry, that 0.5 milliamps is going to go straight through the feedback resistor. And so now I know what the voltage difference will be here because I have the current. So I times R gives me the current from here to here, and then that means I can tell you what the output voltage will be. So this output voltage is negative 0.5 volts. Remember, we know this voltage right here is 0. That tells me everything because I have the current in the resistor, I have the 0 point here. I can solve for that voltage at that node. Okay, I can solve for that. I'm just going to show it to you really quick. You can review it later. V out minus V in. I'm sorry, it actually should be the negative of that. So I'm going to do 0 minus V out. That's the voltage difference between these two nodes. You have to take the difference in the direction that the current is flowing. And then you divide that by RF is equal to the current of 0.5. You know RF, that's the 1 kilo ohm. But even if you didn't, you just plug it into the formula there, and you can solve for V out. I'm not going to go through that algebra. Okay, so let's move on, clear. All right, so if you understood that, now the rest should be easy to talk through. There's going to be a whole bunch of... Okay, so now let's look at this first one. When we have this again grounded, we are forcing this node to be 0 volts. Can you tell me the new voltage, the output voltage for this configuration? We're just going to take 1 minute to do it. You're doing what we did before with the voltage difference divided by the resistor. Then you're going to find the current through the 2 kilo ohms. Remember, you have 2 branches now. And then you'll find V out. I'm going to give you the shortcut. Negative I times RF equals V out. Anybody have it yet? Okay, I'm going to help you out. This first one would be 1.2 milliamps. How did I get that so quickly? And this is going to be 2 milliamps. I'm just doing 10 divided by 5 because this is 0 here. So it's 10 minus 0 over 5 kilo ohms. Okay, so 10 milliamps here, and this is 12 divided by 10. So that's 1.2 milliamps. Once we get to this node, what happens? What current do we see? they combine, okay? So we all see that this will become 2.2 milliamps. That's what's going to go through the 2 kiloohms. And we'll multiply that by 2 kiloohms. Now, the shortcut is that milliamps and kiloohms will cancel each other out. This is 10 times 10 to the negative 3, and this is 10 to the positive 3. 1,000 times 1/1000 just equals 1. All right, so now we end up with 2.2 times 2. So it's 4.4 volts. And that's V out. I'm sorry, negative 4.4 volts is V out. Okay? Negative 4.4 volts. Now I want you to notice there is a relationship between the 12 and the 10 and the 4.4. It's not obvious what that relationship is. In the next examples, it will become more obvious, but these configurations will allow you to do arithmetic on the input voltages. You will have a fixed relationship between the output voltage and the input voltages. You can add them, subtract them, you can divide them, you can even do calculus. You could integrate and do derivatives. So that's OpAmp crash course. Okay, let's clear all the drawings and move to the applications that we're interested in. Here's a fantastic application for us. So what we're doing here is looking at a digital input. Okay, 4 bits, zeros and ones. Now, a 0 is just considered to be open, and a 1 could be a closed state. Okay, look at this. This is on, off, open, closed, and that's going to be my 0 and 1. We don't always have to have the 0 and 1 represents a voltage, one high and low. It could also be an on-off state. So here we have it. Now I'm going to represent the number 1. Or actually, let's just do 0. All of the D bits are 0. Tell me what the current through the 20 kilo ohm resistor is.
0.
Perfect. And the output voltage will also be 0 because it's going to match the, well, it's going to be equal to the current times the resistor here. Okay, so V out, and you see in our table, is 0. Now, let's connect the 0. Let's close it. Now tell me what the current is through the 20 kilo ohms. Do the math really quickly. I need you to see that there is, I'm going to annotate
Is
this.
it 0.05 milliamps?
Okay. Does anybody agree with that value? We're going to look at this path. There's no other current path. So we have 100 kilo ohms in series with the 20 kilo ohms. Okay, but to tell you the truth, we don't even need to think about that because we know this is a voltage of 0 and this is 5. So we have 5 volts over the 100. That's, you just divide 5 by 100, that's 0.05. Okay, 0.05 milliamps. And now that's going to be going through 0.05 milliamps is going through the 20 kilo ohms. Now you see the numbers were picked out so that everything works out nicely. The 20 times the 5 over 100, that's 1 over 20 times 20, right? So it's equal to 1, and the kilo cancels out with the milli, so you end up with 1 volt. And remember, it's the negative. Okay, so we have negative 1 volt for a value when D0 is closed for a binary value equal to 1. I think you can see the logic of what's going to happen here. I'm going to just do one more. I'm going to do number 2. And that means we close this and we open this. So when we have a 2, the same thing happens, but now what happened with my resistance?
Decreased.
It's decreased by a half, which means it doubles my current, which means it doubles V out. Now I'm at 2 volts. All right, now let's just do a number that's a little bit less simple, so we can see that this is going to work right for us every single time. Let's do 6. Or is that too complicated? Actually, let's do 3. Yeah, let's stay a little closer to the simple numbers. So both of these are closed now. All right, and now you're going to see that this is a parallel connection. And I don't know if you remember your parallel theory, but what we have is a total resistance, okay, of 150. What we do is we take 100 times 50, and then we divide by the sum of 150. That's how you combine parallel branches, and it's actually 100 divided by 4. So you can punch that into your calculator. I'm sorry, it's 100 divided by 3. If you punch that into your calculator, you'll see that that becomes 100 over 3. And just a little shortcut for you guys. If you go on to do circuits, when you have parallel branches that are multiples of each other, you can do this. 50 is the same as 200 ohm parallel branches. Oops. Okay, look at this. Here. 50 is the same as 200 ohm parallel branches, and so whenever you have the same number, the same value in parallel branches, you just divide the number by the number of branches. You divide the resistor value by the number of branches. So if I have 2 hundredths, and then I'm putting that in parallel with another 100, that would mean the net resistance is 100 divided by 3. 100 divided by 3. And so I want to show you something. If I have 25, and this is the key to the rest of the circuit, how can I rewrite that in terms of hundredths?
Fifties. Oh,
50s,
I guess.
but I want it in terms of
together.
hundredths.
So
Use a rule that I just taught you. If you have the same value of resistance in parallel branches, you just divide that value by the number of branches that you have. So here I'm going to divide 100 by 4 branches. This is 100. Each branch is 100. So this 25 is the same as 400 ohm branches in parallel. So if I connect the 25, okay, look at this number. It is the 4 bit. If I connect the D2 and leave everything else open, that is the binary number 4. So there are 400s here. So that's actually, it's 4 times smaller, the resistance, than this guy. And that means it's 4 times bigger the value of current and 4 times bigger the value of the voltage. So I didn't even finish the problem of threes. Forgive me. I get excited about these things. Can't even keep my head straight. So here's got D1 and D0 closed. I told you that this is actually 200s in parallel. So now we'll see 300s in parallel, which means that the total resistance is a third of what it was when we just had the value of 1. So that means it's 3 times the value of the voltage, 3 times, and there it is, V out. I am building myself an analog voltage converter. I start with the digital and I end up with the analog. And I can control exactly what values I get. I can control this. How do I control these numbers from 0 to 15? You change this resistor. If I wanted to do from 0 to 7.5, I would just need to make that resistor bigger. I'm sorry, smaller actually. Because the current times resistance gives me my voltage. You see what I mean? And what if I wanted to make my increments smaller? I would change these resistors right here. I would change these resistors. All right, so this is exactly how we do binary weighted D to A conversion. This is one example of a method of converting from digital to analog. I'm going to pause here. Any questions? Okay, so this is the most depth I'll probably get into with regard to the circuit analysis. Once you've understood one deeply, you don't need to get into the details of the others. You just need to see the big picture. So here's the symbol for what we just went through. Okay, and why isn't this used all the time? Well, the reason is because it is actually pretty hard to get a wide range of resistors that have exactly the right relationship. I don't know if you realized from your lab experience that you only had a few to work with. There are some industry standard resistors, and they follow a certain pattern, 47, 33, 1 kilo ohm. And so there's just certain numbers that they will produce in mass. But even those have a tolerance level. You realize that? So you can get something that's labeled 25 ohms, but it's really more like 26.1 or 25.8. There's a tolerance, a margin of error. So that is not the best design, believe it or not, because of the errors that we have in our manufacturing. Okay, so they have improved on it using this configuration, which we could try to get into easily, but I'm not going to bore you with it. It's the same principle of adding currents, but it's a little bit more clever design so that all you need is one resistor. And that reduces your error. Of course, there's still going to be some slack. There's still going to be some error, but it reduces the amount of error. Okay, you can have one company produce very carefully crafted resistances at one specific value, and that's going to help your device. So how, I'll just really quickly show you how this is going to operate. I'm not going to do too much analysis of it though. If I close my D0 bit, I'll have a value of 1. Okay, so actually it is a double throw switch. So you're here at 1. If I close it to the right, if I move it to the right, I'm going to be at 0. Both cases will have current flowing. This is my reference voltage. In the case where everything is shifted to 0, you will have current flowing through here straight to ground. And then it's going to split into this branch here, again straight to ground. So you will have the path going through all of these resistors straight to ground. Now what happens at the voltage output? When you're throwing all of the current to ground there, the voltage output will be 0 because there'll be no current path through my 2R resistor here. Now let's throw one switch to 1. What happens? You've got current for all the other switches going to ground this way. Then you've got current from this branch here going through the 2R, and it is the only current that is feeding the 2R there. Okay? And the other, if I change the closed switch to D1 and open D0, again, I'm going to have the current flowing through these resistors down through 2R into the node here. But look, I have actually only gone through 2 sets of resistors instead of 1. Instead of 3. So I've reduced the number of resistors that I go through, which will increase the amount of current through this resistor here. Okay, so that's the operating principle. Okay, and it should increase it by a factor of 2. It should decrease your resistance by a factor of 4. All right, so having said that, okay, this is where I did do some explanation of it for you. And again, you can look through these slides yourself if you're very interested in it. But this explains it in more detail. Okay.